Welcome back to another explainer brought to you by Forge College. I'm so excited you're here. In our last session, we answered the big question, what is proof of history? We saw how it acts like this brilliant cryptographic anchor, a sequence of hashes proving time actually passed. But today, we're taking that out of the abstract math realm and onto the factory floor. As part of our advanced Solana concepts track, today's explainer is PoH time-stamping mechanics. We're going to see exactly how that abstract hash sequence transforms into deterministic timestamps that bring absolute order to a chaotic, decentralized network like Solana. So, why does all this matter? Well, let's start with a classic network headache. What happens when transactions arrive out of order? Picture a massive sports stadium where the network validators are the referees. Because of network lag and latency, these refs are watching the exact same race, but from totally different vantage points. Without a centralized clock, how on earth do they agree on who crossed the finish line first? Honestly, they act like confused referees trying to untangle a photo finish without a camera. It's just total chaos. To solve that chaos, here's our blueprint for today. 1. The ordering problem. 2. The conveyor belt clock. 3. Ticks and checkpoints. 4. Stamping the transactions. 5. The validator race. And finally, 6. The golden rule. Let's jump right in. Starting off with section 1, the ordering problem. Okay, we know consensus requires everyone to agree on the sequence of events, right? But how do we actually bridge the gap from a continuous chain of hashes to a reliable ordering system everyone trusts? Well, we have to ditch flawed wall clock time and replace it with a deterministic timestamp. Think about it. The clock on your computer can drift, or it can be tampered with. It's subjective. But a deterministic timestamp? That's a highly objective, reproducible numeric counter tied directly to our hash chain. Since the sequence is mathematically bound, validators can independently agree on the exact order of events without ever looking at a real-world clock. It's a real game changer. Moving to section 2, the conveyor belt clock. Okay, let's dive into this. To really wrap our heads around these abstract functions, let's use a mechanical analogy. Imagine a massive industrial machine powering a conveyor belt. Every time the proof of history generator cranks out a sequential hash, it physically carves a permanent notch onto this belt and moves it forward. The key here? This belt only moves strictly forward and it's irreversible. You literally cannot skip a notch, and you definitely can't speed up the belt without doing the actual math, which, by the way, any observer would instantly catch. Because this belt moves with such ruthless mathematical precision, the physical position of any notch on that belt effectively becomes our raw timestamp. All right, section 3, ticks and checkpoints. Having thousands of raw notches on a belt is awesome, but we need to make it readable for the network validators. Let's go through the parts list together. First up, the sequential hash chain. That's the belt itself, giving us an implicit monotonic counter, basically a steady 1, 2, 3, 4. Next, we've got ticks. Think of ticks like the minute marks on a clock face, discrete markers thrown in to give us granularity, so we don't get completely lost counting millions of tiny hashes. Then comes the sign checkpoint. Picture the machine operator physically stamping their signature onto a specific notch, anchoring it to an official network leader. And finally, the transaction mix-in. This is the actual data hashed right into the belt, proving a user's transaction is included. The whole shebang. Now notice the separation of labor here because it's absolutely crucial. On one side, verifying the hash chain position, those notches on the belt, is purely CPU bound. It's cheap, strictly sequential, and any computer on the network can easily reproduce it. But on the flip side, verifying a signature requires a standard asymmetric crypto check. That relies on trusting an authority, like our machine operator. The real magic of proof of history is how it neatly separates that undeniable mechanical ordering from the trusted stamps placed on top of it. Which brings us to section 4, stamping the transactions. Let's put this blueprint into action on the factory floor. Our machine is chugging along perfectly. At hash 1000, transaction A comes down the chute and gets mixed in. It basically drops like a ticket onto that exact notch, forever giving transaction A a raw timestamp of 1001. A little later, at hash 1100, a tick is written, our minute mark. Then at hash 1200, transaction B is mixed in, scoring the timestamp 1201. Finally, at hash 1500, the network leader signs a checkpoint, validating everything that just rolled by on the belt. The order is completely undeniable. A happened before the tick, which happened before B, which happened before the signature. Next up, section 5, the validator race. So let's shift back to the real world, where network lag loves to mess up our perfect factory floor. Remember our totally confused referees from earlier? Say a transaction C is mixed in at hash 2001 and D is mixed in at 2002. Because of network latency, some validators halfway across the globe might actually get the data packet for D before C. In a normal system, that's going to cause a huge argument. But with proof of history? No way. When validators replay the conveyor belt, they'll see right there that C's ticket is stamped at 2001 and D's is at 2002. The deterministic notches instantly resolve the dispute, no matter how the mail arrived. But wait, what if someone tries to pull a fast one? What if the leader tries to sign conflicting checkpoints to maliciously alter history? Well, the system is totally prepared for that. If a leader forges stamps, the validators just replay the hash belt, and the mathematical positions simply won't line up with the forged signatures. Verification fails instantly. The network realizes the leader is acting up, tosses out the bad data, and triggers the protocol's fault-handling rules. The math literally protects the history. And finally, Section 6, the Golden Rule. We've covered a ton of mechanical ground today, so let's boil it all down to one golden rule. Chain equals order, ticks equal granularity, signatures equal anchor. That right there is a profound engineering truth. This system willingly trades the impossible dream of perfectly synced global wall clocks for something way better: mathematically undeniable relative ordering. The chain is the unyielding sequence. The ticks give us readable chunks, and the signatures anchor it all to network authorities. So, what does this all mean? How do these perfectly ordered timestamp primitives plug directly into Solana's block production and consensus mechanisms? Well, I'm going to leave you with that exciting question to ponder. To find out the answer, and to dive deeper into this subject and tons of other Web3 topics, head on over to Forge College. It has been an absolute blast guiding you through this explainer today, brought to you by Forge College. Until next time, keep learning, keep building, and I'll see you in the next explainer.